Okay, so I just wanted to let everyone know that we will be skipping the 5-minute break period and we're going to move on to our next presenter. Amanda, are you ready to present?
Yeah, I am.
Okay, perfect.
Just making sure everybody can hear me okay?
We can hear you.
Yes.
Okay, cool. And I'll just share my screen. Can everybody see that?
Yeah, we can see it.
Okay, cool. So hi, everyone. My name is Amanda. I was in track 1 this year, and I'll be going into industrial engineering second year. And throughout the summer, I've been working on the Common Logic Repository, or Calore, and tools for this repository, which contains the largest number of ontologies in the world currently. I'll start by giving you guys some context on ontologies and semantics. Then we can talk about the details of what I've been working on, which has been super interesting for me as a programmer. And so consider this theory called betweenness. What's written under this theory here are what we call axioms, which we can conceptualize as the rules for what makes something between something else. So in this example on the right here, I'm between the yellow hard hat and the orange hard hat. So for the first axiom, we can read it as, for all x, y, and z, if y is between x and z, then it's also between z and x. So if I'm between the yellow and the orange one, then I'm also between the orange and the yellow one. And then the second one is for all x and y, if y is in between x itself, then x is just equal to y, in which we just have that yellow hard hat. And here's another theory called linearity. And we can see that the first two axioms here are exactly the same as the ones that we see in betweenness, but we have two more axioms here, two new ones that we can prove something else with. And so what we can say is that linearity entails betweenness, because whatever betweenness can deduce, linearity can also do the same. And again, it can also do more than that because it has those two extra axioms. And so these theories are important because they define what, say, betweenness and linearity means. In semantics, we try to work towards interoperability, and it helps the computers understand the exact meaning of a concept without any confusion or overlap, and it works toward more seamless and more meaningful communication. And this is especially important, say, for example, between software systems that are trying to communicate and work together, and we have the seamless communication between the software systems. And so this is called an ontology, and all the names in here are different theory names. And so we can have as many theories as we want in this ontology that describe some sort of concept. This is called the between ontology, and we can see that it's organized into a hierarchy-like structure, which starts with betweenness at the bottom as a root theory, and then branches off into many other theories. And so I circled linearity over here. It's also highlighted in pink. And so if it's at the tip of the arrow, then that theory entails the one at the tail of the arrow. And so if you follow along, say, each different color on this hierarchy, you can see that they actually break off into individual linear chains. And so that's what we call a chain decomposition. And so to find these relationships between theories, we enter them axiom by axiom manually into a theorem prover called prover 9. And so there's different algorithms in which we use, and different ways that we use these, we use prover 9 and to find the individual relationships between two theories. And so this is just a screenshot of Calore and all the different ontologies in there. You can see the between is just one of them. And we have actually over 2,500 of these ontologies. And you guys can probably see how it might be an issue to try and construct a hierarchy for every single one of these manually, especially when just finding the relationship between two individual theories would require time to like input and type out axioms. And so here I've just included a breakdown of my project and what I've been doing. So the first step was to find the relationship between the two theories. We call this the oracle because it's kind of like you just give it two theories and it just tells you the answer, tells you what the relationship is between them. And so underneath that, I have the proof workflow that we do. So first is to check the mutual consistency between two theories. And for that, for example, if you have like, for them to be mutually consistent, we have to be able to combine two theories and be able to construct a model for them. So if you kind of think about, say, two mathematical functions, and then you have like a series of numbers, say like 1, 2, 4, and it keeps going, and then being able to match that, being able to construct that model from combining two theories or two like mathematical functions. It's kind of like the same concept. Um, and and then we also check for entailment, like I was talking about before. It's not always as simple as kind of having the exact same axioms and then having new ones added on there. But yeah, that's kind of how the concept works. And then there's 5 different outcomes that we have from this. So first would be that theories are inconsistent. Second would be that they're independent of each other. And for both of these outcomes, they wouldn't belong in the same chain in the chain decomposition. The other two are the first theory entails the second one, or the second theory entails the first one. And then lastly, would be that both of the theories are equivalent, and they prove the same things. And then the second step of this was to create a program that inserts a new theory into the chain decomposition using the first program, which finds the relationship, or the oracle. And so the objective for this was for it to be accurate and be able to find the correct position of the new theory found in the chain decomposition, and in each individual chain. And the second would be for it to be fast. Currently, this is being all manually done, so we just measure that by the number of manual inputs, and there should be only one manual input of that new theory that's the user is adding into some ontology. And so here is just like a small piece of the code that checks for the consistency from the oracle. And so here we use the what we call the natural language toolkit, and an API that kind of allows us to use Prover9 through Python. And so again, it's just like combining the two theories here and then trying to create a model for it. And then we have another algorithm that uses, again, the same prover to check the entailment. And then this is also like a small piece of the insertion code that we have. And it just uses a simple recursive binary search algorithm. Instead of comparing, like, say, if you're doing numbers and like which one's higher, which one's lower, the higher one would be the one that entails the lower one. And yeah, and then on the right side here is just a piece of the chain decomposition. And then here we have like 3 small chains from the between hierarchy. And then some next steps for this project that I've already gotten started working on, actually, but was made. This was written when I made the presentation. First would be a search tool that allows the user to find an equivalent theory, and you can imagine that this is actually really similar to the insertion algorithm. And then the second search tool that allows the user to input a model and find the closest matching theory for their model. And so this is actually kind of different from the insertion algorithm and like the first search tool that I put here, because it's not like theory to theory. It's like using a model to find a theory that matches your model. Like in the case that the person who is looking for something doesn't know how to write axioms or doesn't know how to use first order logic, but they have some kind of model and they want some theory that is able to match that. And then in this search tool, we'd return kind of like all the closest matching theories. There can be more than one of them, obviously. And the lastly is to automate the implementation to all the Chloride files on GitHub and use this for all the hierarchies, so we can build more organized system and make it more readily used for users. And that's the end of my presentation. Thanks everyone so much for listening. And I'd be happy to answer any questions.
Thank you, Amanda. So judges, whenever you're ready.
Yeah, Amanda, you know, I kind of understand the kind of the the motivation for the research. And so what do you see the real benefit being here, a few years down the road? What will be able to happen? I guess it's mainly in the software world that this will make a difference, but what do you see the sort of the benefit for society here?
I think for this repository, it's continuing to grow, and a lot of people maybe want to have a better grasp of understanding what these ontologies mean and how softwares communicate with each other. And so being able to have these tools, it'll make it a lot easier for people to be able to insert theories or understand what's going on there. Does that answer your question? Or
Well, so if they understand this, what's the benefit of that? What will that do that will make life better for all of us?
Well, it really is within software, it's not something maybe we can see, but if two pieces of software are trying to work together and we have that seamless communication between them, then it'll just make the software much better and much more easily used. And being able to have that this one consistent way of having all different kinds of software being able to communicate with each other would be super beneficial.
Thank you.
Great.
So you're saying that one of the idea is trying to make sure the communication is precise between the platform if you have a different software interface wise.
Yeah. So
okay.
It's kind of like a standard that allows the computers to work with each other.
Okay. Yeah, very cool. Thank you.
Okay, thank you. Thanks so much.